Hello, this is Professor Roman. We'll continue the lecture series on linear algebra. After our digression into Hilbert space, it's time to return to inner product spaces in general. As we did in previous lectures, the field F will refer to either R or C. And we're ready to start chapter 6 of my new book. Just as a reminder, if V is a vector space, then the dual space V star is the vector space of all linear transformations from V to the base field F, and these are referred to as linear functionals. Now, if V is an inner product space, and if W is a vector in V, then the inner product by W function looks like this. This is the notation. The dot is a placekeeper for the variable. This is a function mapping V to F, and when you apply this function to a vector V, it's just the inner product of V with W. This function is linear, and as it's a linear functional, and as it happens, if V is finite dimensional, all linear functionals have this form. Given any linear functional, there's a vector W for which that linear functional is this map. And to understand why this is true, this is a definition that I gave earlier in the lecture series. A function sigma from V to W, and these are complex vector spaces, is conjugate linear if it's additive, and that's what this looks like. And also it's conjugate homogeneous, which means when you pull a scalar out, you have to take its complex conjugate. A bijective conjugate linear map is called a conjugate isomorphism. Now we can get down to business. Let's assume that V is a finite dimensional inner product space. There are various ways actually to show that all linear functionals have the form inner product by some vector. Some approaches are more elegant than others, but not as constructive. Some are more constructive, but not as elegant. So we'll look at several. Perhaps the most elegant approach is the following. We can examine the inner product by function. And in words, I call that tau. Tau takes a vector, W, and produces the inner product by W, linear functional. So this is a map from vectors to linear functionals. Tau of W is inner product by W, which we have discussed, as we have discussed, is a linear functional. This function, tau, is conjugate linear, and the proof is very simple. Tau of a linear combination is inner product by that linear combination. Now we're in the second component here, where we have conjugate linearity, so when we split this up, the scalars come out as their complex conjugates. And so that looks like this, and so this is conjugate linearity. Furthermore, we know that if tau w equals tau w prime, in other words, if inner product by w is the same as inner product by w prime, then w must equal w prime. This we discovered in the last chapter. So this map is injective. Moreover, if V is finite dimensional, then the dimension of V star, which is the dimension of L of Vf, is the product of the dimensions, but the dimension of F is 1, and so we get the dimension of V. So V star and V have the same dimension. We have a conjugate linear map that is injective, and it's between two vector spaces of the same dimension. Just as for linear maps, under those conditions, conjugate linear maps are injective if and only if they're surjective. The proof is essentially the same, and I'll leave that for you. So this map tau is a conjugate isomorphism. Mapping V to V star, tau of W is inner product by W. This is a conjugate isomorphism. Well, in particular, it's surjective and injective. It's bijective in particular. And so for each linear functional f, let's say, in V star, there's a unique vector, which I denote by r sub f, and I'll explain why in a minute, for which f equals tau of rf, or in other words, inner product by r sub f. I need the bijectivity because I want this to have two properties. For every linear functional, there is a preimage, and the preimage is unique. This fact is very important. It's known as the Riesz representation theorem. And this unique vector, then, I'm going to call the Riesz vector for the linear functional f. I don't know if other people use the term Riesz vector or not, but everybody uses the term Riesz representation theorem, so it's not much of a leap. So what we have shown is, again, that every linear functional on a finite dimensional vector space, inner product space, has the form inner product by its unique Riesz vector. This is not constructive at all. It doesn't tell us how to find the vector. It's elegant and very instructive because it uses maps. It uses linear maps to do this proof, to prove that there's a unique Riesz vector for every linear functional. This demonstrates that linear maps are extremely important and often can be used to produce very elegant types of proofs. To be a bit more constructive, we can find the unique Riesz vector as follows. Certainly, if f is the zero linear functional, then the Riesz vector is 0. So we can just assume f is non-zero. This is the definition of the Riesz vector. F of v is v inner product with the Riesz vector. And from this definition, it's quite clear that if a vector is in the kernel of f, in other words, if f of v is 0, then v must be orthogonal to the Riesz vector. So the Riesz vector belongs to the orthogonal complement of the kernel Anything in the kernel is orthogonal to the Riesz vector. The projection theorem, because we're dealing with finite dimensional inner product spaces, allows us to decompose V this way. And the rank nullity theorem tells us that since the image of a linear functional is just non-zero linear functional is the whole codomain, which is dimension 1, this is the rank nullity theorem. The dimension of the kernel plus the dimension of the image is the dimension of the domain. And so the dimension of kernel of F perp is, sorry for the interruption. So the dimension of kernel of F perp, if you look back here, is the dimension of V minus the dimension of the kernel of F. So that looks like this, and the dimension of the kernel of F is 1 short of the dimension of V, so you just get 1. So the dimension of the kernel of F perp is 1. Kernel of F perp is one-dimensional, and it contains the Riesz vector. So we can write the kernel of F perp as the subspace spanned by a single vector, and we can make it a unit vector for convenience. And so the Riesz vector is some scalar multiple of this unit vector U. All we have to do now is figure out what the scalar is. Well, a simple computation. F of that vector U is, by definition, U inner product Riesz vector, but now the Riesz vector is AU. The scalar A comes out in front as A bar, and U is a unit vector, that's why I chose it, so this would be 1, so I just get A bar. So the unique Riesz vector is F applied to U conjugate times U, where U is any unit vector in the orthogonal complement of the kernel of F. Well, at least now we have a formula for the Riesz vector. This may not be as constructive as we'd like, because it does require us to figure out the kernel of F, figure out its orthogonal complement, and that's one-dimensional, so the rest is easy. We just grab any non-zero vector and normalize it. But we still have to deal with finding the kernel and its orthogonal complement. There is, and even though this is maybe not as constructive as we'd like, it does have value, theoretical value as well. So it's not something to be shunned. It's worth, this analysis is worth doing. But we can proceed in a whole different way, another constructive way, and that is to start with an orthonormal basis for the inner product space. The Riesz vector then, of course, is a linear combination of these basis vectors. And so when we apply the functional to any basis vector, it is the inner product of UK with this linear combination, and that's just AK bar, because the U's are orthonormal. So the Riesz vector is also equal to this linear combination. This you will see, I think, in most elementary linear algebra books, this formula. In fact, you may not even see this discussion, the entire discussion, after I said that every linear functional has this form. In some of the books I've seen, and I certainly haven't seen them all, the next thing you will see is this formula and say, here's the formula ecce signum, which means here's the proof, basically, that this vector is the Riesz vector. But this derivation that we went through, the elegant proof and so on, is well worth doing to gain a little bit better insight into how mathematics is done, rather than just here's the formula. This formula, however, may be the simplest as far as computing the Riesz vector. You still have to come up with an orthonormal basis, but if you can come up with any basis, you can apply the Gram-Schmidt process. So this may be the simplest, the most direct route to finding the Riesz vector. And I'll give you an example in a few minutes. Incidentally, because we've shown that the Riesz vector is unique, this formula is independent of the choice of ordered orthonormal basis. Here is the formal statement of the Riesz representation theorem. It's exactly what we've discussed so far. We have a finite dimensional inner product space. The inner product by map is a conjugate isomorphism. And so for every linear functional, there's a unique preimage, which we call the Riesz vector. And that gives this formula for F. And these are the two constructive formulas to compute this Riesz vector. So let's test this out. We'll consider the inner product space R3 square bracket x. So these are the real polynomials of degree 3 or less. And we'll take this inner product that, if you may recall, is the inner product for the Legendre polynomials. So we've discussed this inner product before. And let's pick a Riesz vector, x cubed. So that defines a linear functional by integral of p of x times the Riesz vector x cubed. And I'm doing this so that I can test the two formulas we have. We're going to use both of these formulas here to compute the Riesz vector, and it better come out x cubed. So we'll go with the second formula first. Back in example 5.63, we produced this orthonormal set of vectors by starting with the standard basis vectors 1x, x squared, x cubed, and applying the Gram-Schmidt process. These are almost the Legendre polynomials. They have to be multiplied by an appropriate scalar. These are unit vectors under this inner product. So here's the computation of f applied to each of these basis vectors. Remember the formula. We have to apply f to each basis vector, take the conjugate, which does nothing in this case because we're dealing with a real inner product space, and then multiply by ui. So the Riesz vector looks like this. For example, this is f of u1 is 0, so we don't have that term. F of u2 is square root of 6 over 5, so we take square root of 6 over 5 complex conjugate, which doesn't do anything, times the second basis vector. Then the fourth basis, this is 0 again, so we leave out that term. So we've just got this final term here. So it's just two terms to deal with. And then I replace U2 with its value and U4 with its value, collect everything together, and lo and behold, it all cancels out. Well, let's take a look now at the other approach to finding the Riesz vector. The first step is to compute the kernel of f. And this is the statement that this is an arbitrary polynomial in the inner product space. This is a statement that f of this polynomial is 0, so that the polynomial is in the kernel of f. It's helpful to reduce the computation to note that only even powers of x will contribute to an integral like this because the limits are -1 and 1. So an odd power of x, a term that is an odd power of x, will end up, after integrating, having an even power of x. So when we evaluate at both endpoints, we get the same thing. When we subtract, it's 0. So we can reduce an integral like this easily, distribute the x cubed, and keep only the even powers. Then we take the integral, and that's equal to 0. And so we get from this that a3 is a scalar multiple of a1. So the kernel of f consists of the multiples, the scalar multiples of this polynomial, where the these polynomials where the a sub I belongs to R. We need the orthogonal complement now of this kernel, and that consists of the polynomials that are orthogonal to everything in the kernel. And so this is equivalent to saying that the polynomial, which I've called p of x, is orthogonal to these three polynomials. So we compute the three requirements. These are the inner products equal to 0. Again, removing terms that have odd powers of x reduces the integrals significantly. We take the integrals. Now, if you look at these equations, the first one and the third one are linear in alpha naught and alpha 2, and these two together have only the trivial solution. So alpha naught equals alpha 2 equals 0. This middle one, there's cancellation of the alpha 3 terms, and the alpha 1 terms can be combined, and so this tells us that alpha 1 is also 0. So the kernel of f perp is the subspace spanned by x3. And therefore the Riesz vector is a multiple of x cubed. Did I say x3? X cubed. Okay, for some scalar, and we can compute the scalar, which turns out to be 1. And so the Riesz vector is x cubed. So we have two dramatically different approaches to computing the Riesz vector. And fortunately for me, they both come out to be x cubed. The Riesz representation theorem that we have stated applies to finite dimensional inner product spaces. Here is an example that shows that the theorem does not hold in the infinite dimensional case. This is our old friend, the sequences with finite support over the base field f. And here is the inner product. these are the standard basis vectors that we've used many times before. All vectors W in this inner product space have finite support, and so if we take a linear functional in, I guess I should have called this V here. We take a linear functional on this inner product space that has this form, that is inner product by W. In other words, if we take a linear functional that has a Riesz vector, then when we evaluate this functional on this sequence of standard basis vectors, this can be non-zero for only finitely many of the E sub k's. W is, after all, a linear combination of these standard basis vectors, so there only a finite number of them appear in W. So all but those finite number, this will be 0. But we can define a linear functional, which I call G here, any way we want on the standard basis and extend it by linearity. That's the fundamental theorem of linear transformations. So we could define G to send every basis vector to 1, for example. And then it cannot have this form because, as I just got through saying, this type of linear functional is non-zero only on a finite number of the E sub k's. The Riesz representation theorem is quite a powerful tool. For example, suppose that tau is a linear transformation from V to W, where these are finite dimensional inner product spaces over a field F. Then for any vector little w in W, this map, that takes a vector in V, first applies tau, and then you have a vector in W, and then takes the inner product with little w, this is a linear functional. So the Riesz representation theorem tells us there's a unique Riesz vector, which I'm going to write temporarily as R sub tau W. It depends on both tau and W. We're thinking of tau here as fixed, but W is going to vary. It says for any little w in W. So that's why the notation is a little bit asymmetric. There's a Riesz vector, unique Riesz vector satisfying this. So this is the linear functional applied to V. This is V inner product with the Riesz vector. This defines a linear transformation, R sub tau, from the vectors in W to V. Take a little w in W, R tau of little w is a vector in V. So we're going from W to V. We're going in the opposite direction as tau. The reason this is linear is right here, and it's just a straightforward computation, which I would urge you to try. So we have linearity. It's customary to denote R sub tau by tau star. And that gives us a very nice formula. Inner product tau VW is the inner product of V with tau star W. You can move the tau across the comma, it becomes tau star. And this should remind you of a similar formula that we derived some time ago for a matrix. It looks like this, same formula. A star is the adjoint here of A. And we'll come back to that. So here is the theorem. Let V and W be finite dimensional inner product spaces over F, and let tau be a linear map from V to W. Then there's a unique linear map, tau star, from W to V in the opposite direction, defined by this equation. Tau star W, this is V inner product tau star W is tau V inner product W. So this is an indirect definition. There's only one function with this property. And this map, tau star, is called the adjoint of tau. As I mentioned, tau star points in the opposite direction from tau. Also, for two vectors v and little v and little w and w, if I put tau star w comma v, tau star sends w to a vector in v, so this makes sense. But now the star is in the first coordinate rather than the second coordinate. Well, I can fix that by conjugate symmetry. And now I can move the tau star back to where, to the first coordinate, it becomes tau. And then I can use conjugate symmetry again to get this. So this formula says you can move tau star across the comma, or maybe it's better to say it this way. This tells you that you can move tau from the first component to the second component. You turn it into tau star. This tells you you can move tau from the second component to the first component, and again it becomes tau star. So you can move tau in either direction across the comma if you replace it by tau star. Some properties of the adjoint. The adjoint, I should mention, plays a very significant role in the study of the structure of linear operators. In particular, there are some classes of linear operators, very important classes, that are characterized by the behavior of their adjoint. For example, if an operator is equal to its adjoint, it's called self-adjoint. If an operator is bijective and its inverse is equal to its adjoint, it's called a unitary operator. So these are very important. Another really important class of operators are those that commute with their adjoint. They're called normal operators. So we'll get into all that in subsequent chapters, but the adjoint plays a very key role in all of our future discussions, virtually all. The adjoint is conjugate linear. If you have a linear combination of linear maps, take its adjoint, it goes like this. Linear, it's additive but conjugate homogeneous. So when you pull the constants out, you have to take their complex conjugates. This is quite a list of properties. The adjoint is an involution. If you apply it twice, you get back to where you started. Compatibility with composition, if tau and sigma are linear maps of the appropriate types, so you can take the composition, then the adjoint of tau sigma is sigma star tau star. Works the same way as it does for inverses. You reverse the two factors, the two transformations. And in particular, the adjoint of tau to the kth power is the kth power of tau star. If tau is invertible, then the adjoint of its inverse is the inverse of the adjoint. Compatibility with polynomials. If you have a linear operator and a polynomial, then you can form, the operator is called tau, let's say. You can form P of tau. P of tau star is P bar of tau star. So when you move the star inside the polynomial, that's kind of a sloppy way to say it, you have to change the coefficients. You have to take their complex conjugates. If P of x is a real polynomial, then P of tau star is P of tau star. Two more that are important that relate to invariance. If tau is a linear operator on V and S is a subspace, S is tau invariant if and only if its orthogonal complement is tau star invariant. And as to reductions, if you have an orthogonal direct sum, this will reduce tau if and only if tau is, it'll reduce tau if and only if S is both tau invariant and tau star invariant. This is a direct consequence of number 6. And then the restrictions have behaved nicely with respect to the adjoint. Most of this is just straightforward calculation for the conjugate symmetry. We start with this. We can move this linear combination across the comma. We remove the star and get this. So what you might, to convince yourself of this, you might read it the other way. This is equal to this. That's the definition of adjoint. Now we can use linearity, move the operator back, becomes adjoints, combine, move the constant back in, but see what happens is we pulled the constant out of the first coordinate, but we're putting it into the second coordinate. That's why the complex conjugates appear. And then we finally get this. And so we get our formula. For part 2, as to the involution property, if you start with tau double star V, inner product with W, we can use conjugate symmetry to get this. Then we can move we could move this across the comma. The reason it removes a star, it almost sounds like we're using what we're trying to prove, is that if you read it the other direction, if you start with tau star UV, you're allowed to move tau star across, it becomes tau double star. So that's this. And then we again use conjugate symmetry, and then again, this is equal to this. So we get the first is equal to the last for all vectors V and W. And we had a theorem when we early in our discussion of inner product spaces, that if that happens, then the operators are the same. I'll let you contemplate part 3 and part 4, and I left the rest, and 5, and I left the 6 and 7 about invariant subspaces. I left that as an exercise. If you don't practice with this stuff, it's really not going to stay with you. Okay? You have to kind of suffer over all this a little bit. In fact, the whole course, you have to take the initiative. And I've taken a lot of that away from you by going through these proofs. I was advised when I was a student by a professor, whenever you're reading a book, as soon as you finish the statement of the theorem, don't look at the proof. Try to figure it out yourself. Then you can look at it. That's a tough call. That's difficult because most of the time I think you can't figure out the proof if it's, has any real complication. So it's difficult. Anyway, the kernel and image of the adjoint, they are in fact related, as you would expect, I suppose, to the kernel and image of tau. And here's the relationship. The kernel of tau star is the orthogonal complement of the image of tau, and the image of tau star is the orthogonal complement of the kernel of tau. I think those are beautiful formulas that interchange the roles of kernel and image. It follows then that tau is surjective if and only if tau star is injective, and tau is injective if and only if tau star is surjective. As to the proof, kernels are relatively easy to work with. If U is in the kernel of tau star, U is in the kernel of tau star if and only if, of course, tau star U is 0. And that is equivalent to saying tau star U applied to any vector in V is 0. And we can then move the tau star across. So U is, another way to say this is that tau star U is orthogonal to all of V. So U is orthogonal to all of tau of V. In other words, U is orthogonal to the image of tau. And the second equation can be gotten from the first one by replacing tau by tau star and taking orthogonal complements. We will have occasion in a later chapter to look at these compositions, tau star tau and tau tau star. You could think of these as round trips. Go over by tau, come back by tau star, or come over by tau star, come back by tau. And these compositions will come up for us. So I gave you a theorem whose proof I left as an exercise for more practice. The kernel of tau star tau is the kernel of tau. And the kernel of tau tau star is the kernel of tau star. Image of tau star tau is image of tau star, and image of tau tau star is image of tau. You may be depressed at having to memorize these, but it's not as bad as it looks. For the kernels, just keep the rightmost operator. Whatever is sent to 0 by this operator tau here, or tau star, is the same as whatever is sent to 0 by the whole thing. Or put in a different, better way, whatever is sent to 0 by the composition must be sent to 0 by the right-hand operator. Whatever is sent to 0 by the composition must be sent to 0 by the first operator, the right-hand operator. whatever is in the image of tau star tau is exactly what's in the image of the second operator, whatever survives the second operator. Okay, so maybe that'll help remember these things. What about the matrix representations of tau star? How do they relate to the matrix representations of tau? This is very important because if you have a linear transformation tau and you need to find its adjoint, the definition is not the best way to find it. This definition is not constructive. It just tells you it belongs in a certain component of an inner product. The formula is not helpful in actually obtaining the adjoint. But one way to proceed would be to take the matrix representation of tau, find its adjoint, and hope that that will give you the adjoint, the matrix representation of the adjoint. And in fact it does, and here's how this works. I had to rewrite this proof several times to get it as what I hope as transparent as possible. It can be a bit ugly, this particular proof, but I think you'll find this okay. So we have a tau mapping V to W. We take an ordered orthonormal basis for each, one for V, one for W. And we want to make the connection between these two matrices. Since tau goes from V to W, the matrix representation is tau sub BC. Tau star goes in the opposite direction, so the matrix representation is tau star CB. Well, the first thing to do is write out what these two look like. We know what their columns look like. If you apply the transformation to the old basis and you take its coordinates with respect to the new basis. So that's what we did here, and that's what we did here. And we've, as expected, these are reversed because this is CB, not BC. So to get the ijth entry of, say, this first matrix, we have to pick out the ith entry in the jth column. Ith entry in a column is the ith row. So this is what the jth column is, tau uj c coordinates. But C is an orthonormal basis. So if we want the ijth element, first, this is just a column vector, this column vector here, we just inner product it with the ith standard basis vector. That'll pick out the ith entry. Think about the matrix multiplication here. Okay. Now, E sub I is V sub I, that's the ith C basis vector, C coordinates. This is standard basis vector. Now, because C is an orthonormal basis, we've used this many times in the past. The Gram matrix is the identity matrix, and so the standard inner product of the coordinate matrices is the same as the inner product of the vectors. We usually use it in the opposite direction. So we get tau uj vi. Okay. So this is just simple matrix arithmetic all the way up to this last equality, which is a consequence of the Gram matrix formula. We can do exactly the same computation with this matrix representation. You swap B and C, and you change tau to tau star, and the formula is identical. actually I added, there's a little bit of a difference here because you have to move the tau star across at the end. Okay. We don't have to, but I want to. Okay. So if you ignore this last one, these are the same as the previous. Then I take one more step here. Now, we're trying to compare these two matrices, so here's a comparison of their individual entries, corresponding entries. And you can see that they're quite similar, but not the same. Here are the two expressions. So we stare at these and say, how do we change one so that we can get these to be the same? The official formal term for that is tweaking. Well, all we have to do in this first expression is interchange I and j, and that'll give us tau ui vj, and then we have to take complex conjugates. So let's see how that goes. From here, I interchange I and j, and I take the complex conjugate. Okay. That's going to turn this into this. Okay. And here's what happens. I've interchanged I and j and taken complex conjugate. That is equal to this, because if you ignore the bar, if you just ignore the bar since they're the same on both sides, this is the jith entry of the matrix. So to get the jith entry, you would reverse these, you reverse them here. So you get tau ui vj. Now, the bar over this by conjugate symmetry means you can drop the bar if you swap the components. So you get this. So that is the second one. So by taking this equation here, that this first one is equal to this last one, by taking this equation here, that this first one is equal to the last one, swapping I and j, putting a complex conjugate over it, that allows you to change the order of these two components and remove the bar. You can make these two the same. So if we take the jith entry of this matrix, take its complex conjugate, we get the ijth entry of this matrix. Okay. This may seem a bit confusing. It's possible I didn't explain it very well. It may take a little staring at it, reading it over a few times, writing it down yourself. It's not really as bad as the notation looks. You should have seen my earlier versions of this. So the upshot is terrific. It simply says that these two matrices are complex conjugates of each other. They are adjoints of each other. So the matrix of tau star is the adjoint of the matrix of tau. That's very nice because we start with tau, we want its adjoint. We find a matrix representation with respect to any pair of orthonormal bases. All we do is take the complex conjugate, complex transpose. Okay, I'll get it right. Conjugate transpose. It's very early in the morning here. And that's very simple to do, conjugate transpose. So it's very easy once we get a matrix representation of tau to get a matrix representation of tau star, and then we know how to apply tau star because we have a matrix representation for it. So this is constructive. The definition is not constructive. As a corollary, something that we'll refer to later, we'll just read it now and don't worry about it, that the rank of tau and the rank of tau star are the same. And so the nullities are the same if and only if the dimensions of V and W are the same. I would urge you to try to prove this. I think that'd be a good exercise. Example, misspelling here. Here's a 3 by 3 matrix. This matrix, as you know, represents itself with respect to the standard orthonormal bases. So the adjoint of the operator A is represented by the adjoint matrix. And so all I have to do is take the transpose, because every entry is real. So this is the definition of the adjoint. This is A, U, comma, V equals U, comma, A star V. That's the way the formula looks. So we use the constructive approach to getting the adjoint, and then put that value into the definition of adjoint. We get this. And you can check this directly if you've got spare time. Okay. Imagine how this would look if the matrices were 1,000 by 1,000. You would be disinclined to check it manually. If the bases are not orthonormal, excuse me, then this fails. The matrix of the adjoint is not the adjoint of the matrix. And I gave you a simple example here. A 2 by 2 real matrix represents itself under the standard basis. So the representation of the adjoint is the adjoint of the representation, so we just took the transpose. These are facts because the standard basis is orthonormal. Let's try a non-orthonormal basis. The matrix representation of A, you apply A to the basis vector B. This is both the old and the new now. And then you take its coordinates with respect to B, get this matrix, A star B, same type of computation, but you come out with a different matrix. So they're not adjoints of one another. Another reason why orthonormal bases are so important.